Good morning, lads and ladies. Welcome back to Calc 1. Today, I am hoping to do a little bit more practice with that curve sketching section. You guys have gotten a feel for how kind of time demanding those problems can be. I think it would be, ooh, the shirts have holes, lovely. I think it would be worthwhile to spend a little bit more time there. So I want to start there today. And then if there's time, we'll see if there are other topics to explore, but there really isn't a whole lot else that we need to talk about in preparation for the test. Let me turn on my screen share here. What? There we go. And let's just talk for a quick second here. So applied optimization, that's also on exam too. So yeah, I would like to cover this before spring break. We need to cover this before spring break. So maybe, let's see, maybe one more curve sketching problem and then we introduce applied optimization, or maybe the other way around. Let me go ahead and introduce applied optimization. Well, I don't want to confuse you. Let's take a look at one more curve sketching problem and then we'll do the applied optimization stuff. The curve sketching problem, I'll pick one that'll go quickly here this time. Instead of trying to do something that is sort of representative of all the shit you could possibly need to do, we'll just look at a single problem. So let's get over here and start formally. While I'm here also, I'm gonna, I created a Discord for some of my other classes, so you guys can come in and ask questions and chat with each other. It'll look like, no, don't switch. It'll look like this, and I'll post, links to videos or respond to questions, things like that, so you can get really fast answers from myself and from other students. So before the end of the day today, I'll post a link to a Discord for your guys' class. This one's for my Calc 2. But yeah, here we go. Let's do it. This is MAC2311, section 002. It is a lecture. And today is the 3rd of March? Yeah. 3/3/21. Sadly, we are going to miss Pi Day. It just occurred to me the other day that Pi Day is going to be something that happens during spring break. So I encourage you to support and celebrate Pi Day. Today we're going to do more curve sketching. Which is for still section 4.5. And we're also going to look at some applied optimization. Which is section 4.7. So I don't want to waste any time. Let's come in here to the summary of curve sketching shit. This is what we went over on Monday, of course. And let's look at one of these. So, x(e) to the x, this one's fun. But, so if you want to see a problem like x(e) to the x, let me say this really quickly. You will have noticed, hopefully, in the announcements, if you look at the announcement for Monday's class, not only did I post the link to your video, but I also posted the link to my other Calc 1 class. This is a Calc 1 honors class. I moved a little bit quick here, and we got through 2 examples. So there's the example we did with your class here, 2x over x squared minus 1 in that full curve sketching algorithm. And then I went through 2 other examples with this class. One of them was x(e) to the negative x, which is similar to x(e) to the x, which is an example you can read in the book. And then we also did a 4th degree polynomial here that had some really nasty x-intercepts. We spent a little more time there finding the x-intercepts than we really should have. But if you want more examples of that, you can see those there. And then I'd like to look at just maybe one more here. This one might be okay. Nah, it's a little too easy. slant asymptotes. I'm not going to beat you guys to death with that shit. So I'm just going to grab a simple-ish looking one here. Maybe, let's see, I think this one ended up being a little brutal. Let's look at number 6. So this is section 4.5, problem 6 in the textbook, and it just says to sketch the graph of f of x equals x to the 5 minus 5x, right? Yeah. So we got to run through all those things. First, the domain. F is a polynomial here. Remember, polynomials are functions that have only positive integer powers of x. So this guy is definitely a polynomial. And they all have domain negative infinity to infinity. The book uses the following symbol for that. It's a blackboard bold R. It means real numbers, the set of all real numbers. Intercepts. If we want to look for x-intercepts, remember we do that by setting f of x equal to 0. So that means I would be setting f of x, which is x to the 5 minus 5x equal to 0. And this factors nicely. You can factor out an x. And what's left here is x to the 4 minus 5. Not kidding, no. And then x to the 4 minus 5, this can be factored as a difference of squares. It's not super nice, but it is manageable. This is x times x squared minus the square root of 5 times x squared plus the square root of 5. This piece, x squared plus the square root of 5, is what we call irreducible. You may have noticed in your algebra classes of yore that if you have x squared plus a constant, right, x squared plus something positive, those never factor. The roots of this guy would be plus and minus the 4th root of 5 times I. So we don't have to worry about factoring this down any further, but this can be factored down further. Again, using the difference of squares trick, this would be x minus the 4th root of 5 times x plus the 4th root of 5. And then here we still have x squared plus the square root of 5, like this. So my x-intercepts, these are at x equals 0 from this factor, x equals the positive 4th root of 5 from this factor, and x equals the negative 4th root of 5 from this factor. Y-intercept, this always just comes from plugging in 0 for x. So f of 0 here, that's 0 to the 5 minus 5 times 0, which is 0. So the y-intercept is the point 0, 0. In other words, this x-intercept is also the y-intercept. Symmetries. Here, f of x, I can tell you right now, is an odd function. This function is going to have origin symmetry. And the cheat code for that, if you're looking at a polynomial, which this is, and all the powers of x are odd, and that includes the constant term. The constant term has to be 0, because technically that's x to the 0, which is an even power of x. This guy is going to be an odd function. So f of x here is odd, which means we will have origin symmetry. But if you weren't sure and you wanted to check, the thing you do is you look at f of negative x. This would be negative x to the 5th power minus 5 times negative x. And if this simplifies to negative f of x, then you're looking at an odd function. Now, negative x to the 5th power is the same. You raise negative x to an odd power, that's going to pop out that negative, like this. And here, minus 5 times negative x, that's plus 5x. And this might not look like the negative of f of x at first. You look at this thing and you say, well, is this the negative of that? If you force factor out a negative here, you'll get negative x to the 5th minus 5x. And that is negative f of x, right? Because this is f of x. So indeed, odd function, which means origin symmetry. We want to look for asymptotes. It's a polynomial, so there are no asymptotes. Polynomials don't have asymptotes. But it is worthwhile to note the end behavior. Like as x goes to negative infinity, is this guy going to point up on the left or down on the left? Is he going to point up on the right or down on the right? You know, the end behavior dance, like x squared, x to the 4, all of those guys kind of look like this. X cubed looks like this. Negative x cubed looks like this. The end behavior here, because I have a function with a odd degree and a positive lead coefficient, means as x goes to negative infinity, y is going to go to negative infinity, and as x goes to positive infinity, y is also going to positive infinity. So no asymptotes. You could say nothing for this section if you wanted to, but having this end behavior helps us out. It does give us some starting points to help us draw the graph. I think that's all of the algebra type stuff. So if we want to move on next to the calculus type stuff, I'll take a second to pause here if there are any questions on what we've done so far. Okay. Now on to the good stuff. F prime. So this would be increasing, decreasing, and mins maxes. That all comes from your number line for f primed. F primed of x here is the derivative of f of x. That's d dx of x to the 5th minus 5x, which is 5x to the 4 minus 5. You can factor out a 5, and you get x to the 4 minus 1 in parentheses like this, which can then be factored as a difference of squares. It's x squared minus 1 times x squared plus 1. Again, this piece is irreducible because it's x squared plus a positive constant, and this piece can be further factored as a difference of squares. This is 5 times x minus 1 times x plus 1 times x squared plus 1, like this. So my critical numbers, which are the things that go on the number line for f primed, are x equals -1 from this factor, and x equals +1 from this factor. This guy doesn't give me any critical numbers because he's never equal to 0. Remember, critical numbers are places where f primed is equal to 0 or where f primed is undefined. So this thing is a polynomial. It's never undefined, but it is equal to 0 at these two numbers coming from these two factors. So the number line for f primed just has -1 and +1. And so I'd like to know within each of these regions, is my function increasing or decreasing? And that will help me figure out what's going on at -1 and 1. To the left of -1, we could test x equals -2. F primed of -2, what is that? Well, if I plug -2 in here, this piece is always positive. It's a 5. Vertical number. Critical number. So the critical numbers here are -1 and +1. And that's what I've marked on my number line, -1 and +1. So if we test -2, if we plug -2 into f primed of x, that's this expression. This is positive. This is just a constant 5. -2 minus 1, that's -3. So this piece would be negative. -2 plus 1 is -1. That's also negative. -2 squared is 4. 4 plus 1 is 5. So this would be 5 times -3 times -1 times +5. There's 2 negatives in there and 2 positives in there. Negative, negative, positive, positive. You multiply all of those and you get something that is positive. So my function must be increasing from -infinity all the way up to -1. Between -1 and 1, I can test x equals 0. So f prime of -2, sorry, we said this is positive. F primed of 0, if I plug 0 in here, I'll have 5 times 0 minus 1 times 0 plus 1 times 0 plus 1. That's 5 times -1 times 1 times 1. That's -5. This is definitely negative, which means my function between -1 and +1 is a decreasing function. And then to the right of 1, I could test x equals 2. I want to know, is f primed of 2 positive or negative? So if I plug 2 in here, I'll have 5 times 2 minus 1 times 2 plus 1 times 2 squared plus 1. That's 5 times 1 times 3 times 5. All of those are positive. So this guy is positive, which means we return to being increasing here. Next, we want to sort out concavity and inflection points. I guess before I do that, I should state what's going on here. So what sort of feature does the graph have here at -1? If I go from increasing, yeah, perfect, thank you. All right, Stephanie and one other person here. If we go from increasing to decreasing, you're both correct. That's going to be a local max. And if I go from decreasing to increasing at +1, that means I must have a local min. All right, concavity and inflection points. F double primed of x, that's going to be the derivative of f of x, of f primed of x, which is the d dx derivative of, easiest to work from this form, 5x to the 4 minus 5. I could differentiate any one of these forms to find f double prime because these are all equivalent ways of writing f primed. But this, I would need to use 2 product rules on. This, I would need to use 1 product rule on. This and this are the easy ones to work with. I'll just work from here. So if you differentiate 5x to the 4, you're going to get 20x cubed. And the derivative of -5 is 0. So the only place where f double primed is equal to 0, or undefined, kind of what we're doing here is like finding critical numbers for f to put on the number line for f primed. We find critical numbers for f primed to put on the number line for f double primed. The only places where f double primed can change sign is if it's 0 or undefined. And that's at 0, right? The only place where this guy is 0 is at 0. He's never undefined because he's a polynomial. So the number line for f double primed And in practice, this is the nice way to do it, where you can get the number line for f primed and f double primed on the same page. That way you can kind of look at all of this stuff at once. It's right here at 0. So to the left of 0, if I test x equals -1, f double primed of -1, that's -1 cubed times 20. That's -20, which is less than 0. It's negative, which means we're concave down. And to the right of 0, if you test x equals +1, f double primed of +1 is just 20, which is positive, which means f there is concave up.
So would that mean that 0 is the inflection point?
Yeah, good. There's an inflection point at 0 because we go from concave down to concave up there. It's perfect. Now what I'm going to do is take all the information from these two number lines and put them on a single number line that will allow me to draw the shape of the function f of x. I'll hold here just for a second in case anybody needs to copy anything down. IP stands for inflection point. It's a place where the concavity changes. So concavity, remember, concave up is like looking like this. Concave down is looking like this. And a point where the concavity changes is called an inflection point. All right, if you need a screen cap, grab it fast. Here we go. So the shape of f. I'm going to draw one big number line. And on it goes every number from any of the previous number lines. So my number line for f primed had -1 and 1. My number line for f double primed had 0. So we put all of those here. And then I'm just going to kind of, what's the word when you take a bunch of things and kind of reorganize them into one space?
Condense.
Condense. There's another word for it too. I don't need to bother you guys with my vocabulary issues, but we're going to, yeah, take all the information from these two number lines and condense them into a single number line, giving us the shape of f. So to the left of -1, everywhere to the left of -1, f of x is increasing. And everywhere to the left of 0, f is concave down. And increasing concave down, that's a shape. I know that shape, right? If you're increasing and you are concave down, then you look kind of like this, like the square root function or the natural log function. Those are all increasing concave down. That shape is increasing concave down. At -1, I know I go from increasing to decreasing. But if I'm still to the left of 0, I'm still concave down. So here f would be decreasing, but still concave down. So decreasing concave down looks like this. And you can see if you put two pieces together that look like this, where they join is going to be a local max. And that's what we said earlier. There's a local max here. The point is -1 comma f of -1. I'll come back in and fill in what f of -1 is in a minute. I haven't done that computation yet. Between 0 and 1, right? So at x equals 0, we switch to being concave up. But between 0 and 1, that's still in here. So f is still decreasing. but now we're concave up, which means this had to be an inflection point. And I'm going to want the y value of that inflection point also. It's 0, comma, oh, we actually know, right? 0, comma 0, that's the y-intercept. So I know exactly what that point is. And the shape here, if I'm decreasing and concave up, looks like this. And then finally, to the right of 1, that's where f switches back to being increasing. It stays concave up everywhere to the right of 0. So to the right of 1, we are still, or we are increasing now, but we're still concave up. So increasing concave up, that looks like this, and that means this must be a local min, and that's at 1, comma something. So the last little thing I'd like to do is find the y values at these local mins and local maxes. So the local max at x equals 1 has max value f of 1, and f of x was x to the 5 minus 5x. So f of 1 is 1 to the 5 minus 5 times 1. So that's 1 minus 5, which is negative 4. So this is negative 1, comma, negative 4. That's the local max there. And then the local min at x equals 1 has min value f of 1, which would be, oh, did I do this backwards? I'm so sorry. This should be a negative 1. Yeah. So this is negative 1 plus 5, which is positive 4. I'm so sorry. Yeah, we're plugging in negative 1 here. I wrote 1 there. It's negative 4. That's a little small, isn't it? At x equals negative 1. So we plug in, I'll just rewrite it here, f of negative 1, which is negative 1 to the 5 minus 5 times negative 1, which is negative 1 plus 5, which is positive 4. And the local min is over here at x equals positive 1, so that is the one that would be 1 to the 5 minus 5 times 1, which is 1 minus 5, which is negative 4. All right. So that's that whole procedure, done relatively quickly. Now that I have the shape of f of x, I can draw my graph. I have these 3 points, and I also have my x-intercepts, which we can use from the first part. So let's go ahead and do it. Let's draw this graph. In addition to those, I have my end behavior, which can be useful as well. So here we go. Some points I know to be on this graph. 0, comma 0. 1, comma negative 4. Like this 1, like this negative 4. Call that 1, comma negative 4 right there. We also have negative 1, comma positive 4. So 1, comma positive 4 right there. And then I had these x-intercepts from the very start, remember. I had intercepts x equals 0, 4 through to 5, negative 4 through to 5. About how big is the 4 through to 5? This is something we should be asking ourselves. The 4 through to 4 is the square root of 2 is about 1.4. So the 4 through to 5 should be a little bit bigger than 1.4. In particular, it's to the right of 1. So we'll call that here. This is the 4 through to 5. If you need to use your calculator to get an estimate for these, that's understandable. And then we also had our end behavior. We know that this function goes down on the left and up on the right. I know that this is a local max. I know that this is an IP. I know that this is a local min. I know that this is an x-intercept. This is an x-intercept. So kind of now I have this skeleton that I can use to draw the graph. This isn't an IP. I'll just draw it like this because it's also an x-intercept. So you just kind of put the bits together. Doesn't have to be perfect. The important thing is that we get the concavity right. So you see this is concave down, and then here it switches to being concave up. And we stay concave up over here, and then we go up like this. This point right here is -1,4, and it's a local max. This point down here is +1, -4, and it's a local min. And this point right here is 0, 0. And it's an IP, it's an inflection point. So this would be 10 out of 10, full marks on the test. And there will be at least one problem like this on the test. I'll probably make things easier on you by like giving you some of this information. Yeah, the domain, intercept, symmetry, or say like, don't worry about this stuff. But then creating those number lines, putting them together into the number line for the shape of F and sketching your graph, that's the main thing that I'm going to be looking for on the exam question that relates to this section. Any questions about this example? Excuse me. Just one second. So the next thing we're going to talk about is applied optimization, but I need to clear up my nose. All right. Last call for questions on this example. You guys see what I mean when I call this an inflection point? Everywhere over here, the shape of the graph is like this. It's concave down. Water would run off the side of it. And everywhere over here, to the right of that, this is concave up. It would like collect water. That's what we mean by an inflection point. It's a place where that concavity changes from going like this to going like this. So let's talk about optimization. Really, there's nothing new in this section. It's just another one of those places where we take what we've learned in the past and kind of put it together into something. Specifically, the challenge here, I think, is the applied part. So optimization, this just means finding mins and maxes. These are real world min-max problems. So things like, I have a certain amount of fence and I want to enclose the largest area possible. Or I have a certain amount of material to make a box or a can or some shaped object, and I want to enclose the largest volume possible. Or maybe I need to enclose a certain amount of volume and I want to minimize surface area. So the things you're going to need here are some geometry formulas, some implicit differentiation, stuff like that. I think the best way to get comfy with these is just to look at a few problems. So I'm going to jump right in here. Kind of like related rates, they're going to suggest that you go through those first 3 steps where you read the problem carefully, draw a picture, and introduce some variables. All right, remember those are our first 3 steps for related rates problems. Oftentimes, don't worry about the letter Q here, but oftentimes the idea is going to be to solve and eliminate one of the variables to make your differentiation simpler, to get everything down to a single variable problem, which you can then differentiate and find a min or a max for. And generally speaking, we're looking for an absolute min or an absolute max. There is one theorem here that's going to be useful. So let me go ahead and introduce that theorem. If f of x is increasing everywhere to the left of c, x equals c, to the input x equals c, and decreasing everywhere to the right of c, then what must be going on at x equals c? I want you to think again about that first derivative test. If you're increasing to the left of c and you're decreasing to the right of c, then what feature do you have to have at x equals c? I'll get it here.
A local max.
It's true that we have to have a local max. Then f of x, but don't write that down yet, has, let me use the letter here, and, right, the indefinite article, and absolute max at x equals c. And the keyword to getting absolute out of this instead of just local is the word everywhere. Right? So if your function is increasing, 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 decreasing, 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 and never does anything else, then that local max must also be absolute. And similarly, if f of x is decreasing everywhere to the left of x equals c and increasing everywhere to the right of x equals c, then f of x must have not just a local min, but an absolute min at x equals c.
Is there a difference between finding an absolute and local min or max? Like from an equation or something?
The process is the same, but then if you want to find an absolute max, you need to make sure it's the tallest point anywhere on the graph. So it certainly is possible. How do I say this? If your function is restricted to a small closed interval, a closed bounded interval, then the way you find the absolute max or absolute min is to find all the local maxes or local mins, and then compare the value of the function at the endpoint. Take the biggest of all of those, that'll be your absolute max. The smallest of all of those will be your absolute min. But in this setting, our function won't usually be restricted to a closed bounded interval. And so if there is an absolute max, it will be the largest of all the local maxes. And if there is an absolute min, it will be the smallest of all the local mins. But in general, that's not true. If you look at just the function that we graphed a second ago, this only has one local max. And so we might be inclined to think that that's the absolute max, but it isn't, because this function goes up and up and up and up on the right. So this function doesn't have an absolute max, nor does it have an absolute min. This is the only absolute min. Sorry, this is the only local min. So we might think that it's the absolute min, but this function goes down and down and down forever. So it's not, this function has no absolute min. So yes and no, kind of if you're looking for the absolute max or absolute min for a function whose domain is not restricted to a closed bounded interval, you should find all of the local extrema. But then also think about the end behavior for that function, because that function may not even have an absolute max or an absolute min. In practice, the problems that we're going to be working in section 4.7 here, you'll usually be able to rely on this theorem. Usually there will only be one min or max, and it will be the absolute min or max, whatever it is you're looking for. But if you want to be certain, the thing to do is to think about the graph of that function. So I'll try to kind of walk us through this and make sure that that question has a good feeling answer by the end of class. But I don't think there's a super simple way to answer that. I would say that the procedure for finding the absolute min and absolute maxes that you'll be looking for in this section is the same as the procedure we use to find local mins and local maxes. You're going to look for critical numbers. But then you do need to be a little bit careful about making sure that the thing you found really is the absolute max. So let's do it. Let's look at one or two.
So can there only be either an absolute max and an absolute min? There can't be like both of them on the same graph?
Oh, no, you certainly can have both. Yeah, let me just here really quick, I'll sketch a quick graph that has both. This function, right, even if it's just defined from like -1 to 1, this function has an absolute max here.
Oh, I meant on an unbounded graph.
That's a more subtle question. So if you don't have a restricted domain, is it possible to have both an absolute min and an absolute max? Yes, it is. I like that question, so I want to give a good answer to that too. Hold on with me for a minute here. Trevor's question was, well, what if your function doesn't have a restricted domain? Is it possible to still have an absolute min and an absolute max? The answer is yes, but it depends on what you mean by unbounded. If the graph is unbounded in the sense that mathematicians use that word, then the answer would be no. If the graph goes up and up forever on either side, then you can't have an absolute max. If it goes down and down forever on either side, then you can't have an absolute min. But it is possible to have behavior like this, where I have an absolute max here and an absolute min here, even though the graph here is so a mathematician wouldn't call this unbounded, but the domain is unbounded. The domain isn't restricted. So the domain here is still all real numbers, but we do have both an abs max and an abs min. But you notice there's no arrow like pointing up, or there's no arrow like pointing down. If either side has an arrow pointing up, then you can't have an absolute max. And if either side has an arrow pointing down, then you can't have an absolute min. So in that sense, if your function is unbounded, then you cannot have either. But if you're talking about something like this, where just because the domain is unbounded, you can still have both. An example, this is actually the graph of the function x over x squared plus 1. He has both, even though his domain is all real numbers. Does that answer the question?
Yep.
Cool. All right, sweet. So let's get back to this. I'll just take the first example from the textbook here. They say a farmer has 2,400 feet of fencing to fence off a rectangular field that borders a straight river. What dimensions maximize the area? To enclose the largest pasture possible and one side doesn't require fencing because it's along a river. and I should say the largest rectangular pasture possible. On one side doesn't require fence because it's along the river. What dimensions do this? So here's the situation. I've got a finite amount of fence. I want to enclose the biggest pasture possible. You can kind of draw a picture here. So if your river is over here, then your fencing might look like this. The trick is going to be to come up with a formula for the area and try to find the absolute max for that function. So the area, I'll call A. This dimension I'll call X, and this dimension, excuse me, I'll call Y. The area is X times Y, right? Length times width. And that's what I want to maximize. The other bit of information that I have has to do with how much fencing I've got available. I've only got 2,400 feet of this stuff. So I know that the perimeter, at least the part that needs to be fenced, has to add up to 2,400. Now, clearly, I want to use all of this fence, right? You could say it has to be less than or equal to 2,400 if you wanted. But we know if we want to enclose the maximum amount of area, we shouldn't have any fence left over. What's the perimeter? How much of this thing needs to be fenced in terms of the variables X and Y?
2x and 2y.
We gotta be a little bit careful because this side length down here is along the river. And I'm not worried about my cows going out this side because they can't swim. So I
2x
don't
and
need fence over here. So I've got 2y, right? Y here and a y here, but I've only got one x. So I know that 2,400 is going to be equal to x plus 2y. Yeah, very good. The challenge with finding the max of this function right now on its own is that it has two variables. I don't know how to differentiate that. I can't, there's not really much I can do here. I could differentiate like implicitly with respect to x, but what I want is something that I can like make a number line for. I want to be able to do the normal thing. And to do that, I need to get rid of one of these variables in the function a. And that's where this guy comes in. So this is the object that your book calls Q. It's the quantity that you want to minimize or maximize. This is called the restraint or constraint. Sorry, not restraint, constraint. So I want to maximize this function subject to this constraint. The way I'm going to do this, I'm going to solve this equation for one of those variables. It's easiest to solve it for x, so I will do that. I get 2,400 minus 2y is equal to x. And now I can substitute 2,400 minus 2y in for x in the area function. So what does that give me? That gives me a equals, instead of x now, I'm going to write 2,400 minus 2y times y. And this is now a function of a single variable, so I can take its derivative, find mins and maxes, right? all the normal games. I think it's worth multiplying this out. I would write it as a of y to emphasize that it is now a function of a single variable y. So this is function notation. And this would be negative 2y squared plus 2400 times y. This is the function that I need to now find the absolute max of. So we take the derivative. A primed of y is going to be negative 4y plus 2400. And the critical numbers for a of y are places where this is equal to 0. A prime is never undefined because it's a polynomial. And this thing is equal to 0 if 0 is equal to negative 4y plus 2400, which is equivalent to saying 4y equals 2400, which means y has to be 600, right? Dividing both sides by 4. And in theory, we're done now, because I've found the y value that makes this derivative equal to 0. And so we're hoping that this y value is the absolute max for this function. But I need to check that. So I'm going to make my number line. So this is the number line for the function a prime. I've only got one critical number, so I'll just put it right in the middle here. If we test something to the left of 600, like 1, then this is negative 4 plus 2400. You do want to be a little bit smart about choosing your test points here. Y equals 0 would not be a really wise test point to use, because I'm not interested in a pasture that has height like one of the dimensions 0. You want to make sure whatever you're using for your test points are viable values for the variable in question in the real world problem. So I'll test y equals 1. And if you plug 1 in for y here, you get 2400 minus 4. A primed of 1 is, which is 2396. In particular, it's positive, which means that the function a is increasing everywhere to the left of 600. And if we test y equals, say, 601 over here, a primed of 601 is negative 4 times 601, which is 2404, negative 2404, plus 2400, which is negative 4, which is less than 0. So we're decreasing everywhere over here. So a primed is positive everywhere to the left of 600 and negative everywhere to the right of 600, which means a is increasing everywhere to the left of 600 and decreasing everywhere to the right of 600. So y equals 600 is the location of the absolute max for a of y. And now we just have to go back and answer the question. So we know that when y is 600, this area is maximized. they asked us, what are the dimensions that provide the maximal area? Y is one of those, right? So 600 is one of those, but we need to know what X is also. So finally, when Y equals 600, we can use the constraint equation to solve for X. We have 2400 equals X plus 2Y. That was our equation relating X and Y. I can plug in 600 for Y, so I get 2400 equals X plus 2 times 600, which says 2400 is equal to X plus 1200. Subtract 1200 from both sides and you get 1200 equals X. So Y equals 600, X equals 1200. Those are the dimensions that maximize the area of this pen. All right. So I'll zoom out a little bit and try to get as much of this in one shot as we can. If there's any single pieces that you want to look at, let me know. Kind of here's where the solution really starts. Maybe I can afford to come in a little bit. There we go. Now this is how all of these applied optimization problems go. You draw the picture, label the side lengths or label whatever sort of dimensions are relevant to the problem. So here I knew I wanted to maximize the area and my pen was rectangular. So it's got a width and a height, or a length and a width, whatever you want to think about it. Write down the equation for the thing you want to maximize. And then also write down the equation that relates your two variables to each other. This will usually be a constraint, like you only have so much material, or you need to enclose a certain amount of area, that sort of thing. Then you solve the constraint equation for one of the variables. It doesn't matter which one. Here, this one was easier to solve for X, so I solved for X, but I could have done this by solving for Y. After you've solved the constraint for one of the variables, you substitute that back into your quantity, the thing you're trying to maximize or minimize. In this case, we wanted to maximize the area. So once I solved this for X, I plugged that in for X here, and that gave me this. Now you have your quantity you want to maximize expressed as a function of a single variable. That means you can differentiate it and find critical numbers. Once you've found those critical numbers, you make your number line, find your absolute max or absolute min, whatever it is you're looking for. Make sure that you actually found that thing. That's this test here is still worth doing. And then you go back and answer the problem. Just make sure you're giving an answer to the question that was asked, not just finding a max or a min for some function. Okay. Questions on this? Okay, let's see. I think we have time for one more. So we can grab. Sure, why not? This is a fun one. So we're going to say that the cylindrical can has to hold 1 liter of oil. I'm going to write this down. Example. Must hold 1 liter of oil. Find the dimensions which minimize the material cost for the can. It almost seems like we don't have enough information, right? It's like, okay, what the fuck do you want me to do? In order to get to a place where we have a clear problem to solve, we need to understand what they mean by minimize the material costs. They're talking about minimizing the surface area of the can, right? How much does it cost to make a can? Well, if we're just talking about the cost of the materials, then we're talking about the amount of metal that needs to go into this. You guys are probably too young to remember this shit because everything now is made out of plastic. But back in the day, oil really did used to come in like these soup cans. So the idea is to find the dimensions of the soup can that allow it to hold 1 liter, but uses the least amount of metal to make. Now, this can is going to have a height. I'll call it H. And it's going to have a radius. I'll call that R. I'll draw this as a solid line on it. Radius R. Minimizing the material cost means minimizing the surface area. So I need to know what is the surface area of this thing, and I also need to know what is the volume. I know that the surface area, the easiest way to think about this is to pop the top of the bottom can off. And you realize it's made up of 2 circles and also a rectangle. All right, so you pop these off. This is the top, this is the bottom, and this is the bit that goes around the middle. This is still H. These are each circles of radius R. What is this dimension, the long dimension down here? Can you guys visualize what's going on? Imagine you take a soup can, you open it with your can opener, you pop off the top, then you turn it over, open around the bottom, pop off the bottom, and then you take some very sharp scissors and you cut straight through the middle and you unroll it. This middle piece, this middle piece here would unroll into this, and here's your top and here's your bottom popped off. How long is that middle piece?
Would it be the diameter?
It's not the diameter. So the diameter is the length straight across here, but it's something like that.
The
Imagine I cut it.
circumference?
Yes, the circumference, right? If I cut right here and then unroll, the distance you're seeing along the top is the distance all the way around this top, which is the circumference, which is 2 pi times the radius. So each of these circles, this guy has area pi r squared. This guy has area pi r squared because they're circles, right? The area of a circle is pi r squared. And this guy has area height times circumference, which is 2 pi r times the height. So my total surface area, I'll call this S, is pi r squared plus pi r squared. That's 2 pi r squared plus 2 pi rh. And this is what I want to minimize. My constraint is the volume. I was told that the volume has to be 1 liter. This thing has to hold 1 liter of oil. So the volume of a cylinder like this, can anybody reason their way to the volume of this cylinder? Think about it in its not unrolled state. What is the volume of this thing?
One liter?
It's true, on the one hand, it does have to be 1 liter, but in terms of the variables R and H, what is the volume? Don't feel bad if you don't know this. If you have something that has a cross section that is constant in its area, you just take the area of the cross section and you multiply by the length. So this is going to be like the area of this circle times the height, which is pi r squared times the height. So 1 has to be equal to pi r squared times the height, because the can has to hold 1 liter. Everybody with me so far? I don't think they specified what units they want the, no, they didn't specify what units they want the lengths in, so I'm just going to leave this here. But they have some pictures that'll help you visualize the surface area a little better, right? Popping off the top and the bottom, and then kind of unrolling this. You've got the circumference here, which is 2 pi r, and the height here, and then here's your top and bottom. So I want to minimize this subject to this constraint. These are the two sort of things I'm going to hold on to. Like in the last problem, the way I'm going to do this is by solving the constraint for one of these variables, plugging that in here, so I have a function of a single variable here, then differentiating, setting equal to 0, finding the min or the max, blah, blah, blah. Here I'm looking for a min, right? The easiest variable to solve this thing for is h. So this guy tells me that 1 over pi r squared is equal to h. So I can rewrite the surface area as S equals, what was it first? I'll write it down, 2 pi r squared plus 2 pi r, and then h, which is 1 over pi r squared. All right, yeah, 1 over pi r squared. This is now a function of one variable, r, so I might rewrite it in that function notation. S of r is 2 pi r plus, and now this I can clean up a little bit. The pi's will cancel. One of these r's will cancel, and I'll just be left with 2 over r squared. I'm sorry, 2 over r, fuck. Sorry, 2 over r. One of the r's cancels. So I've got an r here and an r squared downstairs here. All right, so this is like 2 pi r over pi r squared. The pi's cancel and one of the r's cancel. So that leaves me with 1 r downstairs and just the 2 upstairs. And before we differentiate, it might be worth rewriting this as 2 pi r plus 2r to the negative 1. That'll make our derivative a little easier. In the pi r squared. Oh, thank you. Let me see, 2 pi r squared, right? Yeah, this should be a squared. Thank you. You're 100% right. Thank you, thank you. All right, so this is our surface area as a function of the radius. So to minimize this, we find the critical numbers. S primed of r, the derivative here is now going to be 2 pi times 2r plus 2 times negative 1 times r to the negative 2. And we can clean this up. This is 4 pi r minus 2 over r squared. And in order to solve this thing equal to 0, find where this is 0 and where this is undefined, I need to have a common denominator. So I'm going to do that. The common denominator is going to be r squared. And if I multiply this piece by r squared over r squared, I'll get 4 pi r cubed. So I have 4 pi r cubed minus 2 all over r squared. That is S primed of r.
For the exam, are we gonna have to know like the formulas for area or surface area, volume, etc.?
Yeah, I would say that these formulas from geometry are things that you should know at this point. If they're not things that, they are things that you should learn. I won't put any geometry formulas on the test that you wouldn't need in the homework. So make sure that you remember the geometry formulas like area of a circle or surface area, that sort of thing, from the homework problems, and you'll be good on the test. I won't drop anything new on you there, but I will expect you to remember the ones from the homework at least.
Okay.
So then our critical numbers for the function S of r come from the bottom being 0 and the top being 0. So r squared equals 0. That's true if and only if r itself is 0. So he's one of our critical numbers. And then the other one, if I set the top equal to 0, I have 4 pi r cubed minus 2 equals 0. We can add the 2 over. That's 4 pi r cubed equals 2. Divide over the 4 pi. That's r cubed equals 2 over 4 pi. That's 1 over 2 pi. Which means that r, there's only one real solution here. R is the cubed root of 1 over 2 pi. So these are the critical numbers. Now we know that r equals 0 is not going to be our guy, right? I'm not interested in an oil can whose radius is 0. So you can use some logic to deduce that this is probably our dude. But to make sure that he is what we want him to be, we should still set up our number line. It can be tempting to make assumptions here. But the healthy way to solve these problems is to be careful. So I'll make my number line for S primed. I'll put 0 over here. And I'll I'll put the cube root of 1 over 2 pi here. All right. In order to sort out what's going on in the middle here, I need to test something between 0 and this. I'm not interested in anything on this side. I really don't care about negative radii. Doesn't make sense to say the radius is smaller than 0. So between here and here, what do we have? I honestly don't know how big this is, right? Pi is about 3, so this is 1 over 2 pi is about 1/6. The cube root of 1/6, I really don't know. But we can take a guess and say that it's probably bigger than 1/10. So we could try plugging in 0.1 for r. If you want, you could use a calculator to estimate this just for fun. Let's do that. So let's take 1 divided by parentheses 2 pi, close parentheses, hit enter, and then raise this to the power of 1/3, right? So parentheses 1 by 3, close parentheses. 0.33333. It looks like the yeah, the cube root of this is about 1/3 as far as the calculator can tell here. I don't quite trust that entry mechanism, so just to be triple sure, if we want to, never hurts. What I want is the cube root of 1 over 2 pi. Yeah, it's not quite right. Yeah, so 0.54. But certainly the 0.1 is smaller. So this is what I've done. This is about 0.54. So in here we could test r equals 0.1. If I plug in 0.1 for r here, again, I'll use my calculator. I'm looking at 4 pi times 0.1 cubed minus 2 all over 0.1 squared. So this is my s primed function with 0.1 plugged in. It's negative, right? It's like negative 198. Definitely negative in here. S prime of 0.1 is about negative 198. In particular, it's negative. And then to the right of this, you could just test 1, right? Test r equals 1. S primed of 1 here. That's 4 pi minus 2 over 1 squared, which is 4 pi minus 2. You know that pi is about 3, so 4 pi is about 12, so this is about 10, which is definitely positive. So the domain of my function is 0 to infinity. Less than 0 is not interesting. And I am decreasing everywhere to the left of this number, increasing everywhere to the right of this number, which means this guy must be an absolute min. We find that S of R is minimized or has absolute min at R equals the cube root of 1 over 2 pi. So that's the radius that minimizes my surface area, subject to the constraint that the volume is equal to 1. To find the height, we plug this R value back into the constraint, which is the equation that tells us how R and H are related to each other. So what we have is 1 equals pi times the cube root of 1 over 2 pi squared times h, which I can now solve for h. The mechanics of solving for this, it depends on how comfy you are with the algebra, so I'll try to be a little bit careful here. Let's first clean up the right-hand side. This is 1 equals pi times 1 over 2 pi raised to the power of 2/3, right? The cube root is the 1/3 power, and then we're squaring that, so that's the 2/3 power times h. If you take 1 over 2 pi and you raise it to some power, 1 to that power, so this is the same as saying 1 is equal to pi times 1 over 2 pi to the 2/3 times h. All right, this is like 1 to the 2/3 over 2 pi to the 2/3. 1 to the 2/3 is 1. So now I can multiply this over. Let me come up here, be a little conservative with my space. This means I've got 2 pi to the 2/3 equals pi times h. And now I can divide over the pi. So this is 2 pi to the 2/3 divided by pi equals my height. Sorry, 2 pi is in parentheses there. Yeah, sorry. There is a little bit more that we could do here. You could call this 2 to the 2/3 times pi to the 2/3 and then combine the powers of pi. But I would be happy with this. If you give me this, I won't complain. So this is it, the radius and the height that minimize the surface area. And you better believe that back in the 20s, 30s, 40s, 50s, when Pennzoil and all those other companies were doing their manufacturing, they absolutely did this calculation to ensure that they weren't spending more than they needed to on the material for their oil cans. I assure you, if you go find like some vintage store, the repurpose project, you look for one of these old oil cans, it will have this radius and it will have this height. The main group of people that do this sort of work are called industrial systems engineers, ISE. If you're an ISE major, this is your future. This and considerably more complicated versions of this. All right, I think that's all we have time for. We've actually gone a little bit over, so I appreciate you guys' patience, but that gets us through a few examples of these applied optimization problems. I will be putting together study guides and homework for you guys to work on over the break. And next time we come back, we will look at a little bit more applied optimization. And I'll try to do a bit of a review. So I know that you remember, of course, that your test is going to be the first day we come back from break. And that means that our only opportunity to do a real class review is going to be Friday. So we have finished all the material that we're going to have on the test. The test is going to cover everything up through 4.7. And it will be on the first day you come back from break. So please on Friday, our last class here before break, bring questions that you want to work for the review. Anything that's going to be kind of driving you nuts or that you're nervous about showing up on the test, those are the things that you should bring to me on Friday. And yeah, that is it. So I hope you guys have a lovely rest of your day, and I'll see you on Friday.